Assalamu alaikum dear students. I hope you are all fine by the grace of Almighty Allah. I welcome you all to the 16th lecture of Thermodynamics 2. Lecture 16. The contents of lecture 16 are thermodynamics property relations, temperature and entropy diagram, slope of constant volume line versus constant pressure line on PS diagram, entropy change for ideal gas, entropy change for ideal gas during isothermal process, numerical problems, and conceptual questions and answer. Thermodynamics property relations. So in this topic we will combine the first and second law of thermodynamics. So from the first law of thermodynamics we have dq is equal to du plus p dv. So we have dq is equal to du plus w. So for w we have work done is equal to pressure into change in specific volume p dv. And from second law of thermodynamics we have ds is equal to dq by t for reversible. So as we have discussed that the concept of entropy arises from the second law of thermodynamics. Therefore, the relation for entropy we have included in the portion of second law of thermodynamics. So for general we have ds is greater than equal to dq by t, but for reversible process we take the ds is equal to dq by t. So here we have either greater than or equal to. So for greater than we have for irreversible processes, and for reversible process we equate both left and right hand side. So we have ds is equal to dq by t. So here it is written in the subscript as reversible. So this the expression for entropy is valid for reversible process only. So if we take uh, now consider the above equation as equation 1 and second the entropy equation as equation 2. So if we simplify the second equation we get that relation. So we have taken the t that is in the denominator on the left hand side. So we have left with tds is equal to dq. Now for dq we have utilized the equation 1. So in equation 1 we have given that dq is equal to du plus p dv. So we have replaced the value of dq from second law from first law of thermodynamics. So the left hand side is same tds, and on the right hand side that dq is replaced by du plus p dv. We have used the expression from first law of thermodynamics. Now as we know that this is the generalized expression for the enthalpy. So specific enthalpy is given by H is equal to U plus PV. So if we differentiate the expression for specific enthalpy on both hand side. So for left hand side that is dH, for U it is written as du, and on the right hand side for PV it is dPV. So here we will use the product law for differentiation. So as we know that we are using dH is equal to du plus pdv plus vdp. So here we have used the product law for derivation, that is derivative of second multiplied by first term and second with derivative of first. So the first term is p and dv is the derivative second plus second and derivative of first. So now the term du plus pdv, so that is equal to TDS. So TDS is equal to du plus pdv. So the term du plus pdv is, we have replaced that with the TDS term. So that term du plus pdv, we have taken that TDS term. So on the right hand side they both are same, so we have taken that and replaced it here. So we have obtained a relation dH is equal to TDS plus VdP. So the change of enthalpy is equal to the product of temperature and change of entropy plus the product of specific volume and change of pressure. So if we keep the TDS sign on left hand side and VdP on the left hand side, so we have TDS is equal to dH minus VdP. So these two are the relation we have obtained from these mathematical operations. So the first one is TDS is equal to dH minus VdP, and the second is TDS is equal to du plus pdv. So that is the same one. So these two are the thermodynamic property relations. So sometime you may know these relation as Maxwell equation as well. So when you will be driving the Maxwell equation, so we will be utilizing these two expression for the derivation of Maxwell equation. Temperature and entropy diagram. So here is a TS diagram. So here is state 1 and state 2. So TS diagram, temperature on the y-axis and S entropy on the x-axis. So the process is happening from 1 to 2, and it is mentioned on the graph that it is a reversible process. So now we, in this relation, the purpose is to find the heat transfer. So from the expression of entropy we have ds is equal to q by t. And if we keep the value of q on left hand side, then the right hand side is q is equal to tds. And for process 1 to 2, the ds is equal to s2 minus s1. So as we know that the specific entropy is a state function, so both of these values are known. So to find the heat transfer, we will use the expression T into S2 minus S1. So here it is written in the maroon or red color line that heat transfer is the area under the TS diagram. So graphically, if you want to find the value of heat transfer, then you will be looking at the area under the curve. So beneath here you are seeing the PV diagram for the same process. So we have already discussed that in the previous lecture as well. The if you want to calculate the work from the graph, or graphically you want to calculate the work, so area under the PV diagram will give you the work done. So here we have to remember that area under the TS diagram will give us the value of heat transfer, and area under the PV diagram will give us the value of work done. So here we will discuss the conceptual point as well. So note slope of isochoric process. So isochoric process is a constant volume process. So slope of isochoric process is greater than the slope of isobaric process. Isobaric is a constant pressure process on TS diagram. So if you are given the TS diagram and certain processes are shown on TS diagram, so you should know which curve or which slope represent which process. So here we have an example. So we have a TS diagram and 4 processes are shown on TS diagram. So number 1 is isothermal process. So isothermal process is that process in which temperature remain constant. So that is why the 1 is written. So 1 is a horizontal line parallel to x-axis. It means temperature is constant. For process 2, that is adiabatic process. So for reversible adiabatic process, it is also an isentropic process. So it is a straight line parallel to y-axis at which the value of entropy is constant. So that is a adiabatic process, that is a straight line parallel to y-axis. So as they both isothermal and adiabatic process are straight lines, so they are easy to distinguish. But sometimes the curve process are shown, so they are a bit difficult to differentiate from other process. So at 3, the isochoric process is shown. So the process 3 is an isochoric process. So isochoric process is a constant volume process. And process 4 is an isobaric process. Isobaric process is a constant pressure process. So now that consider that you have given the TS diagram and 2 random slope lines are represented to you, and it is not mentioned which process is which. So you are asked to distinguish that uh, you should classify or tell which is an isochoric process and which is an isobaric process. So here is a step written for you that slope of isochoric process is greater than the slope of isobaric process on TS diagram. So then you will calculate or measure the slope. So here from dotted line it is written that theta 3 and theta 4. So theta value of theta 3 is greater than value of theta 4. So you will calculate the angle from with respect to x-axis, and you will tell that the angle that is greater will have a greater slope. So the line that has a greater slope will represent isochoric process, whereas the line that represent lesser slope than will represent isobaric process. So usually you may be given in a TS diagram and you may be asked to write the name of certain process. So 1 and 2 are easy because that one is isothermal, that is a straight line parallel to x-axis in which temperature is constant, and 2 is also very easy, that is the adiabatic process or reversible adiabatic process in which entropy is constant. So it is a straight line parallel to y-axis in which entropy will remain constant. So for two processes that are curve given to you, you will measure their slope and you will tell that the process that has a larger slope will be an isochoric process and that has a smaller slope will be an isobaric process. So second note is slope of adiabatic process is greater than slope of isothermal process on PV diagram. So similarly, like the TS diagram, PV diagram is also shown here, and certain process are represented on the graph. So first is isobaric process. So isobaric process is that in which pressure remain constant. So it is a parallel line, it's a straight line parallel to x-axis in which pressure remain constant. So for process 2, it is isochoric process in which volume remain constant, straight line parallel to y-axis. So in similar to TS diagram, two process shown by a curved line are also represented on PV diagram. So it is a little difficult to distinguish these process, as on the TS diagram two process 3 and 4, that is isochoric and isobaric process, are uh, somewhat difficult to distinguish. So on PV diagram, adiabatic and isothermal process are little difficult to distinguish. So similarly, you will calculate or measure the slope of those process. So the slope that has the process that has a greater slope will be adiabatic process. So the process 3, that is adiabatic, so you have measured the slope. So the process slope is represented by theta 3 and isothermal process slope is represented by theta 4. So theta 3 is greater than theta 4. Therefore, it is written that slope of adiabatic process is greater than slope of isothermal process on PV diagram. So this is a mathematical proof for the node point 1 that we have just studied on the previous slide, that slope of constant volume line versus slope of constant pressure line on TS diagram. So the question might be asked to you in the examination that show that for an ideal gas the slope of constant volume line on TS diagram is more than the constant pressure line. So this is a mathematical proof. On the left hand side, that's the constant volume, and on the right, that is constant pressure. So we will start. The slope of isochoric process is greater than slope of isobaric process. As we know that TdS is equal to du plus Pdv. So we have just obtained this relation on this the current lecture, that TdS is equal to du plus Pdv. But for isochoric process, that is a constant volume process, therefore dV is equal to 0. So the expression is reduced to TdS is equal to du. So U is the specific internal energy. So the relation for U is CVT, and for du, as Cv is the constant, so it will come out of the derivative. So du is equal to dt, Cv dt. So the relation is TdS is equal to Cv dt. So we divide ds on the right hand side, and we have a relation dt by ds for constant volume, because Cv is the specific heat at constant volume. So the entire expression is enclosed for constant volume process. So that is TdS dt divided by ds is equal to T divided by Cv. So dt over ds represent the slope, because t is on the y-axis and s is on the x-axis. So usually for xy graph, slope is written by dy over dx. That is equal to slope. So similarly, dt over ds is also the representation of slope for TS diagram. Now on the right hand side, we are solving this for isobaric process. So what is isobaric process? Is a constant pressure process. Here we are also using the another expression for the Maxwell equation, that is TdS is equal to dH minus V dP. So that is another expression we have obtained in this current lecture as well. So for isobaric process, it's a constant pressure process, therefore the value of dP is equal to 0. So the main expression is reduced to TdS is equal to dH. So H is the specific enthalpy, and the relation for H is CPT. So for dH is equal to, it becomes Cp dt, because Cp is constant, so it comes out of the derivative. So for dH we have Cp dt. So here we have dH is equal to TdS, so TdS is equal to Cp dt. So we have utilized this relation. So we have replaced dH with TdS. So TdS is equal to Cp dt. So we will calculate for dt by ds is equal to T over Cp. So as Cp is the specific heat at constant pressure, so on the left hand side we have classified the entire term with the constant pressure subscript, so that the relation dt by ds is obtained for constant pressure, because we have solved it for isobaric process, so the pressure remain constant. So on the left hand side, dt by ds for constant volume process, the slope come out to be T over Cv. And on the second equation we obtained the slope dt over ds for constant pressure comes out to be T over Cp. So here we have the first expression for constant volume process slope, and here we have equation 2 representing the slope of constant pressure. So as we know that gamma is equal to Cp over Cv, and the value of Cp is greater than Cv. So Cp is greater than Cv. So as Cp is in the denominator and it is greater than Cv, therefore the overall expression in which the Cp is in the denominator will be lesser. Therefore T over Cp will be less than T over Cv, because Cv is smaller than Cp, so a quantity dividing by smaller value will be greater than a quantity that is divided by the larger value. So T over Cp is less than T over Cv. Therefore slope of constant pressure process is less than slope of constant volume process on TS diagram. That is the mathematical proof that show that for ideal gas the slope of constant volume line on TS diagram is greater than the constant pressure line. So this is a mathematical relation for entropy change for ideal gas. So TDS is equal, so these are two different parallel lines. So you should remember that that is not that uh, you should not jump after this equation on the right hand side. This is a separate portion, and this is right hand side is also a separate portion. So for the left hand side we have already derived this expression TdS is equal to du plus p dv. For du we have Cv dt, inserted this equation on the main equation, so we have TdS is equal to Cv dt plus p dv. So dividing t on both hand side, we have left with ds is equal to Cv1 by t dt plus p by t dv. From ideal gas equation, p over t is equal to r over v. So we will replace that p by t with r over v. So here we will wait for a moment and we will continue this from this equation next to next step on the next slide. On the right hand side we have similar T ds is equal to dh minus vtp, dh is equal to cp dt. So T ds is equal to cp dt minus vdp. We have inserted the value of dh, that is cp dt, into the main equation, and keeping ds on the left hand side, dividing t on both hand side, we have cp 1 over t dt minus v by t dt. From ideal gas equation, v by t is equal to r over p. So here we have replaced the value of ds is equal to cv 1 by t dt plus r 1 over v dv. So here we will integrate the entire expression. So the result is S2 minus S1, that is change of entropy, is equal to Cv natural log T2 over T1 plus R natural log V2 over V1. And similarly on the right hand side, after integrating the expression, we have left with S2 minus S1 is equal to Cp natural log T2 over T1 minus R natural log P2 over P1. We will find another expression as well for the entropy change for ideal gas as well. Here you must remember that these are very important relation to find the entropy change for ideal gas. So if you look closely that the expression one, if I call that if we call that is equation A, and that is equation B. If you look closely to equation A, you will find that the term that is comprised of temperature T2 T1, it include the value of specific heat at constant volume Cv, where for equation B, for T2 T1 term or polynomial, it include the specific heat at constant pressure, so Cp. And for equation 1, we have a ratio of volume V2 over V1, and for equation B we have ratio for pressure P2 and P1. So we will use equation 1 when we have both temperatures and both volumes, both specific volume. So if we have temperature 1 and temperature 2 and specific volume 1 and specific volume 2, and we will use equation B if we have temperature 1 temperature 2 and pressure 1 and pressure 2. So if we have volume and temperature, we will use equation A, and if we have temperature and pressure, we will use equation B. We will also derive another expression or third equation for the change of entropy for ideal gas, in which we will find a relation that does not contain temperature. So the third expression that will be calculated in the upcoming slide will eventually have volume and pressure terms. So we have calculated two expressions for the change of entropy for ideal gas. Now we will solve that if we are solving for isothermal process. So if we are calculating the entropy change for ideal gas and the process is isothermal, then what is the value for that entropy change? So for isothermal process, the both temperature are same, T1 is equal to T2. So the main equation is S2 minus S1 is equal to Cv natural log T2 over T1 plus R natural log V2 over V1. That is the main equation. We have just derived that equation in the previous slide. So if both of these value of T1 T2 is equal, so natural log of 1 is 0. So the change of entropy for ideal gas for isothermal process is S2 minus S1 is equal to R into natural log V2 over V1. Similarly, on the right hand side, the value of change of entropy for ideal gas for isothermal process comes out to be S2 minus S1, that is minus R natural log V2 over V1, because the first term that contains the ratio of T2 over T1 will be cancelled out. So the next term, that is minus R natural log V2 over V1, will be left. So similarly, you may be asked to calculate the value for the change of entropy for ideal gas for isochoric process, isobaric process. So that term will be cancelled out for isochoric process, and for isobaric process that term will be cancelled out. So we have these main equation and we will utilize it for different processes. So for different process, that main equation will be reduced further. So now we will find a relation for change of entropy for ideal gas that does not contain the relation or ratio of temperature. So from ideal gas equation, here we have P1 V1 over T1 is equal to P2 V2 over T2. So basically we have a relation PV is equal to MRT. So M and R are constant, so their corresponding ratio will be same. And solving it for T2 over T1, we have P2 V2 over P1 V1. So P1 P2 are pressure, V1 V2 are the specific volume, T1 T2 are the temperatures. So in the main change of entropy equation, we have del S is equal to Cp natural log. Here we have temperature ratio T2 over T1. So here we have changed the here we have replaced the value of T2 over T1 from for P2 V2 over P1 V1, and the other right side expression will remain same, minus R natural log P2 over P1. So simplifying the equation, del S is equal to Cp natural log. So the product, here we have utilized the law of log, natural log. So we have separated both equation. We have separated both terms, that is natural log P2 over P1 is kept separate with the natural log V2 over V1 term. So here natural log P2 over P1 is common, so that term and both are common, so they are, and Cp minus R, so that is the common term is taken on the left hand side and Cp minus R is in the bracket plus, and the term Cp natural log V2 over V1 is kept same. So as you know that Cp minus Cv is equal to R, so Cp minus R is equal to Cv. So Cp is the specific heat at constant pressure minus R is the general gas constant. So Cp minus Cv is equal to R. So Cv is kept for Cp minus R is equal to Cv. So del S is equal to natural log P2 over P1 Cv plus Cp natural log V2 over V1. So the final relation for the entropy change for ideal gas is del S is equal to Cv natural log P2 over P1 plus Cp natural log V2 over V1. So that is the relation that does not contain temperature term. So we have all three relations. The first one contains temperature and pressure, the second contains temperature and volume, and the third contains pressure and volume. So here we have some conceptual question and answer. So water at 100 kPa 150 degree centigrade receive 75 kilojoule per kg in a reversible process by heat transfer. Which process change entropy the most? Constant temperature, constant volume, or constant pressure? So the answer is, if we look at the constant property lines on TS diagram, the constant volume line has a higher slope than the constant pressure line. So this is just the proof that we have solved in the current lecture, that the constant volume line has a higher slope than the constant pressure line. So thus both the constant pressure and volume process have an increase in T, that is temperature. So as T goes up, the change in S is smaller. So as T is in the denominator, if we increase that value that is in the denominator, so ds, that is change in entropy, will reduce. So if T is in the denominator, we increase that value, so ds will drop. So the constant T, that is isothermal process, so the entropy change will be the most. So the value of entropy change for isothermal process is greatest. So in the TS diagram, when you draw a TS diagram, T and S, and isothermal line is drawn, that is a straight line. So whereas other is our slope P and V, in which we isobaric and isochoric are a slope line, whereas isothermal is straight line. So if the process is isothermal, there will be greatest change in the entropy for the process. So the del S will be maximum for isothermal process, whereas the slope shown for isochoric and isobaric process also show the increase in the entropy, but the isothermal process shows maximum change in the entropy. So a liquid is compressed in a reversible adiabatic process. What is the change in temperature? So as you know that reversible adiabatic process is a isentropic process, so the value of entropy is constant. But you should also remember that this process is applied on the liquid or incompressible fluid. So the change in S or entropy for incompressible substance is given by ds is equal to c by t dt. So according to above equation, if ds is equal to 0, then t is equal to constant. So t will not change during this process. An ideal gas goes through a constant temperature reversible heat addition process. How do the properties V, specific volume, internal energy, specific enthalpy, entropy, that specific entropy, and pressure change? So for that process, that is a constant temperature reversible heat addition process. Constant temperature is isothermal, reversible isothermal heat addition process. So you have already studied the Carnot heat engine. So one of the process, that is reversible isothermal heat addition process, is also included in the Carnot heat engine cycle. So for ideal gas, so it is mentioned that the working substance is an ideal gas. So U and H, that is internal energy and specific enthalpy, is a function of temperature. So for isothermal process, since the temperature is not changing, therefore they both are constant. So from the relation of entropy, so as heat is added to the system, therefore entropy will increase. So as the temperature is constant, so it is an isothermal process and heat is adding to the system. So to counter the heat addition and to keep the temperature constant, so there will be an expansion process. So volume will increase. And as the volume increase, therefore pressure will decrease. Carbon dioxide is compressed to a smaller volume in a polytropic process with the polytropic index is 1.2. How do the properties UHSTP change? They will increase, decrease or remain constant. So U is internal energy, specific enthalpy, S is the specific entropy, T is temperature, P pressure. For carbon dioxide, we consult table A.5. K is equal to 1.289, that is N is less than K. So N is given as 1.2 and the value for K is 1.289 from table 8.5. From this means smaller volume means moving to the left in the PV diagram and thus also up increase in P. So PV diagram is we will moving from 1 to 2 as N is less than K. If N will be greater than K, then the process will be from left to right, that will be increase or decrease in the pressure. So for the current scenario, as N is less than K, that means smaller volume means moving to the left. So for moving right to left, the volume is decreasing. So the process is happening from right to left. So volume is decreasing and pressure is increasing. And for TS diagram 1 to 2, the temperature will increase, entropy will decrease, and pressure is increasing and volume is decreasing. So as temperature is increasing, therefore U and T. So from PV diagram, pressure will increase, temperature will increase, temperature is increased, then S is down. So as temperature is increasing, therefore the entropy value will be decreased. And T and U and H are the function of temperature. As temperature is increasing, therefore specific enthalpy and internal energy will also increase. So here is a numerical problem. The statement is a cylinder piston setup contains 1 liter of saturated liquid refrigerant R410A at 20 degrees centigrade. The piston now slowly expands, maintaining constant temperature to final pressure of 400 kilopascal in a reversible process. So the final pressure is given. Calculate the work and heat transfer required to accomplish this process. So first you should underline the important information. 1 liter, that volume, so that is very important information. Saturated liquid, so in a dome shape initially that is present, okay, it is there. So and process 1, that is on the saturated liquid line, and the temperature here is at process 1, that is 20 degrees centigrade, and the final pressure given is 400 kilopascal, and it is a constant temperature process. So the final temperature will also be 20 degrees centigrade, but as shown in the figure, the phase will be changed. So we will go for the solution. So from the value continuity equation, the mass will be conserved. From the first law of thermodynamics, mu2 minus u1, that is capital U, is equal to q122 minus w122. That is from first law of thermodynamics. And from second law of thermodynamics, m into s2 minus s1 is equal to integration del q by t. So these are the formulae that will be utilized during the solution of this problem. So as R410A is a specially designed refrigerant, so its property table is given in the annexure of your book. So as you go to the table 4.1, for the value in the saturated liquid portion for against 20 degree centigrade, you will find these value for internal energy and specific entropy. So the value is 87.94 kilojoule per kg and 0.3357 kilojoule per kg Kelvin. So from the value of volume 1 liter is mentioned. So to calculate the mass, you will divide the volume with the specific volume. So mass comes out to be 1.083 kg. So for state 2 or final state, we will consult table 4.2. So the value of specific internal energy and entropy are given in table B 4.2 against temperature 20 degree centigrade and pressure 400. So now we will utilize the second law of thermodynamics. We will insert the value and find the value of heat, that is 277.8 kilojoule. Then we will insert the value of heat into the first law of thermodynamics to calculate the value of work. So the value of work comes out to be 73.7 kilojoules. So this is your home assignment. You can read it. So thank you very much. Allah Hafiz.